All right, hello. We're going to do some related rates problems together. If you're in my class, most of these are on the worksheet I handed out to you during our distance education phase of our COVID-19 social isolation in 2020, but they're good problems anyway. So if you're watching this at some other time, um, well, hopefully they'll help you. So, first of all, let's just talk about solving related rates problems. Again, I'm going to put that on big screen. I don't think I have to put the other stuff on big screen because the problems are very large and I think you can read them anyways. So, if you get a related rates problem, the idea is that there's a relation between one rate and another rate. And what you're trying to figure out is what the relation of that one rate of change is to the other rate of change. So the first thing to do usually is just to draw something. It kind of gets you started, gets you going, kind of gets you a feel for what's going on. And then you're going to be given one rate of change. You're going to be given 1 meters per second or cubic centimeters per minute or whatever. And it's going to be related to another rate, and they're going to be asking you what that other rate of change is. So what you have to do is draw it out and make an equation that in a static way relates those two rates. And after you've done that, then you do implicit differentiation style thing where you differentiate both sides with respect to time. And it's almost algebra because you're already given one derivative. And so you've given one derivative and you're solving for the other derivative. So basically you're going to write an equation that relates the quantities, and it could be you make sure anything that changes you have to use a variable for, but anything that's a constant, like the height of a lamppost or whatever, you can just go ahead and put the number in for that because that'll make it easier to have a number in there for the constant. So yeah, and it's going to be something like a trig or Pythagorean theorem, similar triangle, something like that. And then you take the derivative with respect to both sides, the derivative of both sides with respect to time. And then because you already have the derivative with respect to time for one quantity, one rate of change, you'll be able to solve that equation for the rate of change of the other quantity. All right, so let's move over to our document camera and let's get started. This problem I think we already did. A 6 foot tall dude walking 8 feet per second away from a 22-foot tall lamppost. I'm going to go ahead and move to the next one because it's exactly the same problem with some different numbers. And this time we have a 5 foot high dude walking away from a 20-foot tall lamppost at 4 feet per second when he is 50 feet from it. So what are we going to do? We're always going to start with a little drawing, right? We got this, and the lamppost doesn't change. So we're going to put a number in for that. How tall is the lamppost? It's 20 feet tall. 20 feet, right? And we have a 5 foot high dude. Boy, I made this drawing super small. Sorry about that. 20 feet tall. You know what? Let's just do it again. There, now you can see it. So we got a 5 foot tall dude, and we can just go ahead and put 5 feet in there because that's a constant. And then we have a 20 foot tall lamppost. That is also a constant, right? But we're asking about this shadow of this dude right here, right? That's the shadow of the dude. Oops, I made his arms going the wrong way. Anyway, it doesn't matter. The lamppost is 20, he's 5. He's walking at 4 feet per second. So we're going to make this kind of our 0. That's our frame of reference. And that's going to be x. That's going to be the distance from the lamppost. And then this we're going to call s for the shadow. And then it's also asking how fast the tip of the shadow is moving. So we're going to end up needing this measurement as well. And we're going to call that L. Just because that's what I want to call it. So now we have to look at this and relate. We got similar triangles, right? There's a triangle and there's a triangle. And we want to be able to rate those in terms of two variables, one of which we already know the rate of change. And we know that his rate of change, dx with respect to time, the change in x with respect to time is going to be 4 feet per second, right? So that's what we know. And now all we have to do is do similar triangles. So we could say something like, hang on a second. Yes, we can say hang on a second if we need to. So we can, so we got dx dt. I'm sorry. And what we're trying to find is how fast that shadow is growing, right? ds dt. I will get smoothed out here. I've just had so many technical problems today, I just can't stand it. So this is what we're trying to find is ds dt. So we need some equation that relates x to s. And then when we know the rate of change of x, we can use that equation that relates x to s, differentiate it with respect to time, to find the rate of change of s. All right? So we can just do like this over this, right? The ratio of this to this for similar triangles is going to equal the ratio of this, the big triangle, the bottom leg of the big triangle, to the bottom leg of the small triangle, right? So the height, this piece of the big triangle, 20, the ratio of that to that, 5, is going to equal the ratio of the whole bottom, because that's the big triangle, right? X plus S, that's the whole bottom. And then 5, the small triangle has just S right there, right? Okay, I'm going to make sure my 5s and my S's look different, right? Okay, so now the first thing we're going to do is algebraically rearrange this. So we're going to move that S up over there, and we're going to move that 5 over there. So we're going to have 20S equals 5x plus S. All right, the next thing we're going to do is distribute that 5. So we're going to keep our 20s over here, and we're going to have 5x plus plus 5. It has been that kind of day. 5s, okay? Then we're going to subtract 5s from both sides, and that's going to leave us with 15s equals 5x. Then we're going to divide both sides by 15, and that's going to leave us with s equals 5 over 15x. And we can reduce that fraction to 1/3, right? X. Now, we know how fast x is changing, and that will tell us how fast s is changing, right? So we're trying to find ds, dt with respect to time. So then we have to take the derivative of this side with respect to time, right? The 1/3 goes outside. ds dt. Am I still? Oh, I'm off the. How'd that happen? Okay. Oh, man. All right. So we're going to go back up here. We're going to rewrite that. ds dt. You guys you're probably ahead of me at this point. 1/3 dx dt. The x, right? So ds dt equals, we already know this, right? We know that it's 4. So it's going to be 1/3 times 4, or ds dt is going to equal 4/3. And then what's our units? Feet per second. Okay. Hopefully the other ones will go smoother. But we have two parts to this problem, right? So this is part 1. That's the answer to part A. But now we have part B, which is how fast the tip of the shadow is moving, right? Well, the tip of the shadow is just going to be moving the rate of this one moving plus the rate of this one moving. But we're going to start with the static equation. L equals x plus s, right? Nobody's going to fight me on that, right? All right, good. So now we can do the respect to the differentiate with respect to time, and do our little wizardry here. That is all fine and good, right? And we know this and we know that. So dl dt equals dx dt, which was given in the problem as 4, plus ds dt, which we figured out was, where'd it go? 4/3. And now if we take a 3 out of that, so we're going to be left with 5 1/3. I hope you can do that. So the rate of length of the movement, the tip of the shadow is actually moving at 5 1/3 feet per second. Okay, that's B. All right, so that's the first one. Now on to the worksheet. I hope you can read that. I think you're going to be able to. So what we have here is water leaking onto a floor, forming a circular pool. Well, that's not very good, is it? The radius of the pool increases at a rate. Let's draw the pool. I'm going to make sure I stay high up on the paper. So there's our pool, and there's our radius, right? The radius of the pool increases at a rate of 4 centimeters per minute. A rate is what? That's the derivative, right? So we know the change in radius with respect to the change in time is 4 centimeters, where'd it go? Per minute. And now it's a related rates problem, right? So we need to relate the rate of change of the radius to the rate of change in the area, right? So how do you get the area? And then we're doing this when r equals 5. That's the time frame we're actually looking at, right? Okay, so the area of a circle is pi r squared. Well, this I'm going to just write a 1 up here because if you're looking at that CUDA worksheet that I put out, this is number 1. The area equals pi r squared. We already have an equation that has everything we need because what we're looking for is the change in area. I should have written this down. I'm not being very systematic. How fast is the area changing? So we know we've got dr dt, and what we want to know is how fast is the area changing with respect to time. What's dA dt? Okay, so without any work at all, we already have the area equals pi r squared, right? We have r, and we know dr dt. Pi is a constant, and a, what we're looking for, is dA dt. So all we actually need to do is take the differentiate this with respect to time. So dA dt equals d dt of this whole bit, right? Okay, but pi is a constant, isn't it? So we can take the constant out. Pi d dt r squared. Okay, so now we have to, it's kind of the implicit differentiation kind of thing. So what we're going to do is take the we're going to differentiate that, but then we're going to leave a dr dt hanging out on the end. dA dt equals pi. What is the differential of that? It's 2, take the 2 out in front, r, right? And then r goes down to 1, so it's just going to be 2r. 2r, and then we have to leave our dr dt hanging out on the end. All right? Now, we know pi, sort of, right? We never know how many digits, but whatever. We know the r that we're looking for in this instance, and we know dr dt, because those are all given in the problem. So look at that. We actually, in that short amount of space, we actually have everything basically solved. But let's put it in. Let's actually solve the problem, shall we? So we got pi, and then we got 2, and then we got r. R is going to be 5, right? And then we got dr dt. That's going to be 4. So 4 times 5 is 20 times 2 is 40. So dA dt equals 40 what? Centimeters per minute. Is that reasonable? Yes. Oh, look what I did. I made a mistake. I dropped the pi, didn't I? Oh no, Mr. Rollison dropped the pi. That's going to be mess to clean up. Oh, I was off. Oh, I wasn't off the sheet. Good. All right. So that's all that one asked for, right? That's how fast the radius is increasing. That's how fast the area is increasing when the radius is increasing at 4 centimeters per second at a radius of 5 centimeters. That's how fast the area is increasing. So there you go. And hopefully the pi that I dropped isn't spreading that fast. All right, next question. Here we go. And I'm going to leave that on the same page actually because it's another, it's the same question from a different perspective. Oil spilling from a ruptured tanker spreads in a circle on the surface of the ocean. All right, so there we have a circle again, right? The area of the spill increases at a rate, bing, 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 rate. That must be our rate of change, right? 9 pi meters per second per minute. So dA dt equals 9 pi square meters per minute. How fast is the radius of the spill increasing when the radius is at 10 meters? Okay, so how fast is the radius increasing? So they're asking what is dr dt at r equals 10 meters. Okay, it's the same thing. We already did the area, right? Right over there. Area equals pi r squared. dA over dt equals dt. Oops. Jeez. d dt pi r squared dA dt equals pi d dt of r squared. This is exactly the same problem with just a different known variable, right? Equals pi, and then we got to do the differential of that. So that's going to be 2r dr dt, 2r dr, we should put those all in parentheses, dr dt, right? Okay, so now we just got to put in our numbers. dA dt, that's what we know. That's 9 pi equals pi times 2 times r. We're saying this is at r equals 10, right? And what is dr dt? That's what we don't know. So the pi's are going to cancel out, right? 9, and then 2 times 10 is 20. Divide both sides by 20. And 9 over, what am I doing? 9 over 20 equals the rate of change of the radius. So when the area is changing at a rate of 9 pi meters per second per minute, and the radius is 10, the radius is changing at a rate of 9 over 20 meters per minute. I didn't put the units in there. Don't forget the units. Don't forget the units. And that's 2 on the worksheet. Okay, let's do to number 3. Here we go. Oh, now they've switched it up on us. A conical paper cup is 10 centimeters tall with a radius of 10 centimeters. So that's actually going to save us some time here. This is number 3, by the way. So this equals that, right? It's 10 centimeters tall and it has a radius of 10. So it's really going to look like this. The cup is filled with water so that the water level rises at a rate, bing, 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 rate of 2 centimeters per second. The water level is rising. So we're going to have, that's going to be how much water is in the cup, right? And I'm going to do that. That's how much water is in the cup, right? So this, that's going to be H. All right, we're going to call that height because we're going to need to know the height. And so it says the water level is rising at a rate of 2 centimeters per second. So dH, the water level, the height, dH dt, that's the rate at which the height is changing, is 2 centimeters per second. All right. At what rate is water being poured into the cup when the water level is 8 centimeters? So this is at H equals 8. At H equals 8, dH dt equals 2. Okay, because that's the height and that's the rate of change of the height. Now, what's the formula for the volume of a cone? I'm not going to pretend I didn't have to look it up because I did. So the volume of a cone is pi r squared h over 3. Do we have enough information for that? Well, we do. It's a little bit hidden. If this is 10 and this is 10, I don't know if you can see that. You should be able to see that. If that's 10 and that's 10, right? And then this is a similar triangle. And this is a smaller triangle, right? So in the smaller triangle where the water level actually is, if that's 8, that's also going to be 8, right? And you might have to do it if the cup doesn't have the radius and the height equal, you're going to have to do you're going to have to figure out the ratio of that. But it's a similar triangles thing again. But here, they've just told us the radius equals the height at any given water level, right? Because it's 10 and 10. So for us, and for our purpose, we can say R equals H, which is a great help because this problem doesn't actually ask about the radius, what's happening with the radius. It's asking about what's happening with the volume and the height. So we need to set up our equation in a way that it relates the height of the water level to the volume of the water level. And having the radius equal the height just makes things a little bit easier. So we're going to swap that R out for an H just to make things nice. And it does in fact make things nice. Pi H squared H over 3. And we're going to just do our little algebraic voodoo here. And we're going to make this pi over 3, because you can do that, right? Pi over 3, and then h times h squared is what? That's h cubed, isn't it? All right, so now things are looking pretty easy. Because what we're trying to find is the change in volume, right? At what rate is water being poured into? So that's just another way of saying what's the rate of change of the volume over time. So now we have managed to boil this thing down into an equation that has the height of the water related to the volume, and we know the change in height. So if we know the rate of change of height and we know the relationship of the height to the volume, then we can figure out the rate of change of the volume just by differentiating both sides. So dV dt equals dH dt of our formula, or equation, whatever you want to call it. All right. Oops, pi over 3. Okay, so pi over 3 is a constant, so we can pull that outside. So that's going to be pi over 3, and then it's going to be d, that should not put an h there, sorry about that, d dt of h cubed. Okay, you with me there? All right, so then for an implicit differential, we're going to differentiate that and then leave a dh dt hanging out on the end. dv dt equals pi over 3. What's the differential of that? So that's we take that and put that up front, right? 3h squared. So that's going to be 3h squared, and then we got to leave a dh dt hanging out on the end there, right? Okay. Now all we have to do is put in our h. Our h equals 8, right? So here we go. dv dt equals, that 3 is going to cancel out, right? So we'll get rid of that. And we're just going to say pi, and then h is 8, right? And that's going to be 8 squared, so that's going to be 64. And then dh dt, they gave it to us. That's part of the setup of the problem. That's so important. It's related rates. They give you one rate, and you're relating it to the other rate. So dh dt is 2. And the answer to this problem, believe it or not, is 128 pi. And I am going to look at my answer sheet just to check it. I check it every time. Oh, forgot the units. What is the units? That's going to be cubic centimeters per second. And that should have been inside the box, right? But every time I've gone over this, I double check it because that is obviously a lot. That cup is being filled rather quickly, right? Okay, so next problem. A spherical balloon, which of course is hypothetical because no balloons are perfectly spherical, but that's where we're at right now. So we got a spherical balloon, which we'll represent with a circle. Maybe we can put one of those little reflections off the top, kind of make it look like a sphere. Okay, so, and it's going to have a radius. And let's look at the problem. A spherical balloon is inflated so that its radius r increases at a rate. Okay, so there's our rate, dr. That's what we know. It's increasing at a rate of 2 over r centimeters per second. And how fast is the volume of the balloon increasing when the radius is 4 centimeters? So when r equals 4 centimeters, how fast is that balloon? How fast is the volume of the balloon growing? So we need the volume of a sphere, right? And again, I'm not going to tell you that I knew this by heart. I had to look it up. The volume of a sphere is 4/3 pi r cubed. All right. So now we only have 2 variables, right? So that makes it easy. I mean, we don't even have to do any extra algebraic work to boil it down to 2 variables, which you might. But the idea is you boil that thing down to 2 variables that you can relate to each other, and then you can relate the rate of change of one variable to the rate of change of the other. That's what's going on here. So we're ready to go. We're ready to go. dv dt equals d dt, and I'm just gonna, I know we're on problem 4, so I probably don't have to do some of these steps over and over again, but I'm gonna anyways. 4/3 and pi are constants, so we can take them outside of the differential, right? So 4/3 pi d dt of r cubed. All right, Now we got to take the differential of that and then leave a dr dt hanging out on the backside. So dv dt equals 4/3 pi. The differential of that, take that 3 down, right? So 3r, and then we subtract 1 from that. That's 2. And then we leave a dr dt hanging off on the backside. And now you can see that we have all the information we need, right? Constant, constant, constant. R, we're asked for a given R, so that's part of the situational setup. And dr dt, we're given that also. So let's go ahead and put some numbers in. Now one of the other things that's it's a tiny little tricky thing. And it's the sort of thing where if you're kind of nervous about the problem, it might throw you already. But they tell you the change in the radius with respect to time is 2 divided by the radius. And you're like, oh, wait a minute, that's something else. But it's not really, because they tell you the time at which we're trying to calculate the rate of change, right? So it's r equals 4. So for our purposes, at this particular point in time, dr dt equals 2/4, right? Because that's the 4 right there. That's the r, the 4. Okay, so dr dt equals 0.5. That's not too bad, is it? It's not too bad. So now we just got to we got to start to plug in numbers and things. So here we go, dv dt equals, there's a 3 on the bottom and a 3 on the top, so those cancel out. So then we're going to have a 4 pi r squared. So the situation setup is at what radius, right? So r, that's our r. So 4 squared, that's going to be 16. And then dr dt at that same time, at that same place, excuse me, the rate at that moment when r equals 4 is going to be 0.5. And now you can see we're just, at this point, we have stepped back down the ladder one rung into algebra. Actually, we're probably not even in algebra anymore. 0.5 times 16 is 8, right? 8 times 4 is 32. 32 pi. And what's it asking for? It's asking for, I did not, boy, bad form again. It was asking for dv dt. And volume is in cubic centimeters. So it's going to be cubic centimeters. And we're working in seconds. So hopefully, by this time, I didn't write it up there, but you did anyways, because you're doing the job. All right, next one. A 7-foot tall, oh, it's a lamppost problem. We know how to do lamppost problems. They're like old hat for us now. And I think, this is number 5. The other one was number 4, yeah. So this is number 5 on our sheet. And we could do lamppost problems all day now, right? There's our lamppost. And there's a dude walking. And this time he's 7 feet tall. This is a tall guy or girl walking away from a lamppost. So there's our shadow length. And there's our distance from the lamppost. And the lamppost is how tall? The lamppost is 20 feet tall. And the person is 7 feet tall. Okay? And he's walking at a rate of 5 feet per second. So that's going to be this x right there. So the change in x with respect to time is 5 feet per second. All right? At what rate is the length of the person's shadow changing when the person is 16 feet from the lamppost? So it's asking about when x equals 16. But we're not going to start out, we're not going to put in that number until after we differentiate it, because that's one of the variables that's changing, right? And the differentiation is going to change the change. change. I'm a teacher. Okay, so here we go. We got to set this baby up. Similar triangles, right? Similar triangles. And you can use whichever ratio you like. let's do this one. Let's say the ratio of the vertical to the horizontal is going to be the same as the ratio of the vertical to the horizontal. So the vertical is 20, and the horizontal is x plus s, right? That's the whole big triangle. Is going to equal this similar triangle, the vertical part over the horizontal part. All right, so there we go. And you're like ahead of me now, I think. So 20s equals 7x plus s. You saw what I did right there, right? 20s, 7x plus s. Now we're going to distribute the 7. 20s equals 7x plus 7s. Okay, now we're going to subtract 7s from both sides. And so we'll have 13s equals 7x. And then we're going to divide by 13, and we're going to have s equals 7/13 x. So what we have done is we've related the two sides, one variable to the other, and this ratio is going to be true for everything, right? But now we're going to differentiate it with respect to time for this situation with those numbers. But now we're going to take we're going to differentiate it with respect to time. So ds dt equals d dt 7/13 x. All right, and you know the drill by now, I think. dt, pull that constant out, 7/13 dx dt. We know dx dt, it's already been given to us, it's 5. So ds dt equals 7/13 times 5. Which is going to be 7 times 5 is 35. ds dt equals 35/13 feet per second. And I'm just going to double check it. Make sure I got it right. And I did. Good for me. Okay. Let's just put number 6 on the same page, shall we? Number 6. What is the last one? We're almost done here. An observer stands 700 feet away from a launch pad to observe a rocket launch. The rocket blasts off and maintains a velocity of 900 feet per second. Assume the flight can be modeled as a right triangle, so that rocket is going straight up. So how fast is the observer to the rocket distance changing when the rocket is 2,400 feet from the ground? All right, so we have our observer, right? And we have a rocket. We have a rocket pad, a launch pad somewhere over here. And the observer is standing 700 feet from the launch pad. That doesn't change, so we can write the number down. If it doesn't change, you can write the number down. So the rocket's blasting off. Let's draw a little rocket. That's a horrible rocket. Little fins. Okay, there we go. All right, so that's our rocket. And what do we got? What else we got? The velocity, that's the rate of change, right, is 900 feet per second. So let's call this h because that's the height of the rocket, right? But we're going to say h because it's changing. So we're going to say dh dt, the rate of change in height with respect to time is going to be 900 feet per second. And it's asking about the distance from the observer to the rocket. So we're going to call that x because it's just always nice to solve for x, isn't it? All right, so how do we solve this? How do we solve this problem? What's the relationship between these three things? This one's staying constant, this one's changing, and this one's changing. So that is a right triangle, right? That's what they told us. So what do we know about right triangles? We know a squared plus b squared equals c squared, right? And in this case, we know that let's call this g for on the ground, okay? So in this case, we are going to be able to say that x squared, that's that, equals g squared, that's that leg, plus h squared, that's that leg, right? Okay. Now we're going to take the square root of both sides, so we get x by itself because that's what we want. X equals the square root of g squared plus h squared. Okay, so g squared is a constant. It's not changing. So we can safely put the number in right now, which we kind of want to do because we don't want to, if we're, in this situation, it's better to you just feel better seeing numbers because then you know they're not changing. You could do it without, anyway. So we're going to put the number in there. So we're going to say that x equals the square root of, and what's our number? 700 squared plus h squared. All right. And you know these things are easier if instead of using that radical sign, you do them like this. Right? That makes it easier. Now it's pretty clearly the chain rule, isn't it? It is. So what we're going to do is do dx dt. And we're going to have to chain rule this guy. Well, first of all, let's be formal, since this is a video explaining everything. All right, so now we're differentiating with respect to t, so we're just going to do the derivative and leave a dh dt hanging off the end, right? So here we go. It's going to be a couple steps, right, because it's chain rule. So dx dt equals the derivative of the outside, right? So what's the derivative of the outside? We take that and we put it out front. There's no coefficient for us to worry about. So we're going to have 1/2, and then we have the inside function left 700, left just as it is. And then we got to subtract 1 from that, right? Negative 1/2. And then we got to do the derivative of the inside function. That's a constant, so it goes away. The derivative of h squared is 2h, and then we leave a dh dt because h is still changing, so we don't want to forget that, off the end there. Now we just have to do the math. So here we go. dx dt equals 1/2. And now the numbers get big. The process works. Doesn't matter how big the numbers are, the process works. So just take a deep breath, go forward with the giant numbers. So 700 squared is 490,000. Plus, now we've taken the differentiation. We've taken the derivative. So we can put our h value in there now. And this was, what was the problem? I didn't write it down. At h equals 2400. I am not being a very good example at setting the problems up ahead of time. So we know that we need h to be 2400. So if h is 2400, h squared, and I'm doing a little bit unorthodox notation just to save room, it's 5,760,000. That's h squared. Okay, and we're still just putting in numbers. And then we have 2 times 2 times h, which is 2400, times dh dt, which is 900, right? All right. So now I'm going to just, and again, here's some really unorthodox notation. I'm just going to do this and say that all that comes together to be 4,320,000. 4,320,000. All right, 2,400. Let's keep commas in there. They help us keep track of things. Okay, so now we're almost there. Isn't this fun? It's like a nice little puzzle, isn't it? All right, so here's what we're going to do. That negative there is going to put that on the bottom of the fraction, right? we're going to say 4,320,000 times 1/2 is 202,160,000. 2,160,000. All right. And then we're going to add those two together and put them under a radical, which is 6,250,000. All right. And now these are solvable problems with a simple calculator, right? dx dt equals, and we'll just leave this one alone for this particular step. And oh my goodness, look at that. It's almost like somebody set this problem up, isn't it? And then, would you believe that actually comes out to an even number as well? And hopefully you did this before me. That's the whole deal. That's how fast the distance from the observer to the rocket is changing if this rocket, if its height is increasing at 900 feet per second. At a height of 2,400 feet, the distance between this observer and the rocket is changing at a rate of 864 feet per second. And that is how you do those things. And hopefully by the time you've run through these, and hopefully you tried them first and then like did step by step with me if you're still having trouble, hopefully by now you can look at a related rates problem and begin to peel it apart and put it back together in a way that works. And see ya.